Today we're going to talk about measurement techniques and other topics relating to measuring things. It seems like it should be something that's really fairly basic, especially for students in honors bio. However, what I found is that there's always a little bit of nuance that honors bio students don't always get every aspect. And we want to make sure that you don't move on in your education, especially your science education, without making sure that you know those fundamentals. Take notes as you go and make sure you ask me if you have any questions. Okay, so the first component of a quality measurement is, of course, the number. We'll talk about how to make sure that that is the best number we can possibly get. It's also important to include a unit of measurement, and most of the time it's helpful to include what's being measured. So, for example, instead of just saying 50 milligrams, you might say 50 milligrams of aspirin. This is especially important if you're talking about laboratory reports. Though when we start to repeat things, so for example, if you were constantly measuring 50 milliliters of aspirin, milligrams of aspirin, you might not need to keep repeating aspirin. But generally, you want to include it at least initially and, of course, in your materials and procedures. Another important aspect of measuring is determining the interval of our measurement tool. So if we take a look at this measurement tool, we've got not every number numbered. And so since not every number is labeled, we need to figure out what the intermediate lines mean. So you can do that much the same way you would trying to figure out what your interval should be when you graph. So you need to count the value between the labeled lines or the larger lines and decide how many spaces it's sectioned into. So for example, if we look at this, of course the value between 0 and 5 is 5. And although there's only 4 lines between them, there are 1, 2, 3, 4, 5 spaces. In other words, I'm dividing that chunk of distance into 5 pieces, so naturally each line is 1. If we try to figure out what that arrow represents, of course, if each little line is 1 and this line is 10, you have 1, 2, 3, that line is representing 13. Take a second, see if you figure out what this interval is. Of course, it's 5. If we have a distance of 25 and we divide it into 5 spaces, we naturally get each one being 5. Consequently, what's that value? Well, if each one is 5, and this is 25, that puts this at 30, 35, 40, and 45. So, of course, that arrow is pointing to 45, in this case, centimeters. How about this one? This one's a little bit trickier because every big line is numbered, 1, 2, 3, 4. So then we need to divide that and get a fraction of a line. So 1 divided by 5 pieces gives us each one is 0.2. So consequently, what is that value? Of course, it's 4.8 centimeters. Another important consideration to think about when measuring is how we're reporting our digits. In other words, what is our last digit? What degree are we estimating, and what degree are we certain of our measurement tool? So if we take a look at this tool, of course, we're going by ones because it's divided into 5 sections, so each interval is 1. But if we take a look at that line, it's not right on the line. This line is 18, and this line is 19, and that arrow is neither 18 nor 19. We don't want to guess too much and imply that we're able to be certain more than we are, so we always want to make sure that we are only estimating one digit, the last digit in our number. So for example, I am positive that this arrow is somewhere between 18 and 19. I know it's past the 18 line, but it has not yet reached the 19 line. So I am positive that my measurement of 18 centimeters and change is correct. The question is how much change is left over, and that's our estimation. I don't know for certain how much is left over. I can just eyeball what percentage of that 1 centimeter's worth of interval that arrow is represented. So where it lies is an estimation, and I'm going to guess that this one is about 18.7. You may have looked at that and thought, well, it's really more 18.6 or 18.8. We're guessing, we don't know. So that last digit, the 7, is our estimation. In the United States, when we're used to the standard measurement system, or in other words, dividing by fractions, a lot of us might want to go, oh, well, it's 3/4. In science, we don't use fractions. We'll talk more about that in a minute. So we only use decimal points, which means that that last digit is always going to be our estimation. So we're never going to go 0.75 or 0.25 unless we're certain that it's 0.75 and 0.25. So let's practice that a little bit. So we have our measurement tool. We're still going by ones. So where's that line? We know that it's past the 19, but it's not yet to the 20, so we know it's 19 point something. And again, we're estimating what that last digit is, and I'm going to estimate 19.5. Could just as easily have been 19.6, but 19.5 is my estimate. You do this one. Where's that line? So we know it's 5 point something, but here's the deal. I know it's past 5, but it's not yet into 0.2. So then I need to figure out how much is it. So if I'm going by an interval of 2, I know that halfway is 0.1. This is not yet even halfway, so I know it's less than 5.1. So I'm certain it's 5.0 something. I'm guessing 2. That seemed a little bit low to me. I might say 5.05. But remember that last digit is an estimate, so I'm certain it's 5.0. I'm not certain past that. It's also important to keep in mind that our estimates can be a 0. So in this case, to me, it looks like the yellow bar hits right at the 5.1 line. It might not be quite there. It might be 5.09, but I'm pretty sure it's at 5.1. So in that case, I add a 0 at the end to indicate that I am guessing it's exactly at 5.10. So when we want to guess that our estimate is right on a whole number, we add that 0 to indicate that last digit is our guess. Real quickly, let's talk a few other measurement tips before we move on. First one is when you're measuring length of an object that doesn't have a straight edge, we always want to go to the longest point. So in this case, we would line our oval right up at 0 on one side to the very tip, and on the other side we would use some sort of a straight edge to go over to our measurement tool to kind of estimate that. In this case, based on that pink line, I know that it's past the 5.3 mark, but not quite to the 5.4 mark. So I'm going to estimate 5.33 centimeters. This would be kind of similar to if you've ever stood and had your parents measure your height or at the doctor, and they put that bar on top at the doctor's office, or sometimes they might put a book at home to line you up against a doorway or something. That's measuring how far you are so we can get that back, the curvature of your head. This is pretty obvious to most of you, but remember, you can't always get your ruler right up at 0, depending on the shape or the size or where you can fit your ruler in. So remember, if you don't start at 0, you want to make sure you subtract your starting point from your ending point to get the overall length of the object. One last tip on measuring, and that is a lot of the things that you measure aren't two-dimensional. They're three-dimensional, and they could be objects that curve or bend. So to measure the full length of that, depending upon what measurement we're looking for, if I wanted to find out, for example, how tall you were, I'd use the book technique that I mentioned. However, if I wanted to find out how long your spine is, I might put a piece of string from the back of your spine and include the curvature of your spine. And so to do that, I would line a string up around it to make sure I could increase my accuracy. If you've ever been to a fancy store and they do gift wrap for you, they do the same thing when they're measuring the paper. So they'll take a piece of string and wrap it around the box, and so they know exactly how long they need to cut the paper so they don't end up with that annoying situation where you're just a little bit short. And so the same situation applies. The string can take a curved surface and help make it straight. So once you've got the string and you know how long the string is, you can lay that out on a ruler and more easily measure it. I know you learned this in 8th grade, but just in case you've forgotten, when we measure volume in a graduated cylinder, we always want to measure from the bottom of the meniscus, which is the bubble. So in this case, I've got 50 labeled, I've got 60 labeled, and 10 lines between, so of course my interval is 1 milliliter. I know that it's somewhere between 51, 52, and 53. So I'm going to go from the bottom of that. I'm certain it was 52, and I'm going to estimate 52.8 because it's almost up at that 53 mark. And of course, our units for volume is milliliter. Speaking of units, what units do we use in science? I am hoping that in your head you all just went metric, because of course in science we use the metric system. The metric system is really not the accurate term. We actually call it System of International Units, really international system, but it's in French. So we call them SI units for short. System of International Units is mostly metric. There are a little bit of tweaking for science, but mostly metric. And the reason why is that it's based on powers of 10. And since frequently in science we do calculations with our numbers, to try to calculate numbers that have fractions like 1/16 of an inch, or to work with the number of pounds just gets really, really sketchy, really, really fast. And it's way, way easier to multiply or divide by a power of 10 than it is to multiply and divide by 12 inches, or 1/16 of an inch. And it's used most places in the world. And most importantly in science, it is the language of science. It's what scientists have agreed upon using. And when we take a look at one of the reasons why we use it, we're talking about like the vast majority of the world uses some form of the metric system. If you notice, the little sign, I don't know if you can read it, but Antarctica also includes the metric system, which of course is because most of the people in Antarctica are scientists. And just to kind of hit home why it's so important that we use metric, take a look at our numbers. You can ignore the imperial tongue, which is in England. Just look at our American measurement of a ton and a metric ton. To try to calculate and divide by these terms and remember the conversions is kind of crazy, whereas it's super easy to go 1,000, a million, a billion. That's the beauty of the metric system, and of course of this system in international units. So when we measure, we have two kinds of units. The first of which is called a fundamental unit, and that is a direct measurement. So for example, we've decided a meter is a certain amount of space. That is a fundamental unit. We can convert it to centimeters or kilometers, but meter is a particular unit. Gram, second, temperature, those are all our fundamental units. And although it's very, very easy to convert them to other related fundamental units, like kilogram or gram, like going between kilogram and gram, those are the ones we directly measure. In science, of course, we also calculate a lot of measurements. So in 8th grade, you did a lot with density. To calculate density, you need mass and volume. Some volume we can measure directly with a liter. Other volumes, like that of a cube, we need to measure and then calculate. So length times width times height would be a derived unit. Let's take a quick moment to review. When we make measurements, we need to strive to be both precise and accurate. Those two terms are often used interchangeably, but they have very distinct meanings. You can probably get a sense for what the meanings are by looking at this diagram. An accurate measurement is like hitting the bullseye. In other words, it's getting very, very close to the true or the actual value. The accuracy of the measurement relies both on your taking it, so your interpretation of the tool and your carefulness in taking the measurement, as well as the capabilities of the tool. We'll talk more about that in a second. Precision refers to, is your measurement repeatable? And so we want to make sure that we're always getting a measurement that is both true or accurate, and that we're getting it every time. If you had a piece of gunk on your scale, every mass you measured would be off by the weight of that gunk. We want to make sure that that doesn't happen, so we want both accuracy and precision, so we're trying to hit the target every time. When we report our accuracy is where most students have the most problems. We report accuracy using something called significant figures, and it's, like I said, it's really challenging for a lot of students. So the best way I can give you is to imagine that you're taking a tour at a museum, and the docent, or in other words, the volunteer tour guide there, she says, this fossil is 67,000,000.5 years old. And you look at it and you're like, 67,000,000.5 years? How do you know that closely how old it is? And she replies, well, I've been volunteering here for 6 months, and when I started here, that's what they told me, 67 million years old. Of course, she's mistaking what they told her as being a precise and accurate measurement. When the scientists told her how old that fossil was, they were giving her an estimate. And then she tacked on those extra numbers. Remember, when we record an estimate, we only ever report an estimate as the last digit. So when she was saying 65,000,000.5 years old, she was saying that this number was our only estimate, when in fact most of these digits are estimates. And so we know it's in the millions, we know it's pretty close to 65 million, but maybe it's 66 million. It's an estimate. Or it's 67,100,050. We don't know that. We're estimating that. And so by her putting that 0.5 on is implying far more accuracy, because remember, just that last digit should be the guess. So we want to make sure that we're reporting our accuracy correctly. We don't want to imply that our measurements were closer to the target than they really are. So the problem is that quite frequently in science, when we need to make a calculation, we put it into our calculator, and our calculator spits out a number that has a bunch of digits at it. So we weren't able to measure that accurately. But the calculator, because those numbers don't divide nice and evenly, we get a digit that has all kinds of numbers after it. Because of that, we want to make sure that we're not reporting absolutely everything in our calculator, because it's suggesting false accuracy. Our accuracy is limited by our tools and our calculation. In our measurements, different measurements have different capabilities. So in this ruler, for example, the centimeters are labeled 6, 7, 8, 9, and the little lines in between represent millimeters. We can't go much smaller than that because we're estimating if we're between two lines. This tool right here has a capability of measuring the micrometer, which is that little funny shaped U. A micrometer, in 1 millimeter, there are 1,000 micrometer, and this tool can be far more precise. So for this tool, I can use a lot more digits than this one. So this dinosaur example, we're limited by our ability to radioactively date fossils. When the docent reported 67 million point 5 years, she was implying that our aging of the fossil was accurate to the fraction of a year. In reality, radiometric aging isn't that accurate. We can get more accurate than 67, but it's not to the portion of a year. So when the museum reports 67 million years old, the 7 is likely our estimate. So to indicate that, and that it could be 66 million years old or 68 million years old, we rounded to 67, and we just use those extra zeros to keep our place in 67 million years. If I have to calculate something, I get two areas. Each length I'm able to measure essentially to the millimeter. And that last millimeter, the 5 here and the 1 over here, is our estimate. If I multiply the area, I get that big number, and that is implying that I'm accurate far, far greater. That's to the micrometer, not the millimeter. So I would want to round. So there are fancy rules for how it is you should do this, and you will learn those in chemistry. For now, we're just going to use significant figures. So in other words, just stick to the number of digits you started with. It's more complicated than that, but just stick to the number of digits you started with. So for example, this number has 4 digits, this number has 4 digits. So my answer, I would round this to 33.37 meters squared. So if when researchers took a measurement in order to estimate the age of the fossils, they were only able to suggest certainty with 2 digits, but were able to calculate 67,123,004 years. To imply 67 is our maximum accuracy, we would round to 67 and add those extra zeros in for placekeepers to keep it in the millions as opposed to just 67 years. You will learn this in much more detail when you take chemistry class. Let's take a quick moment and review. The last topic we need to talk about with measurements and units is how we convert from one unit to another. As I mentioned, when we talk about the scientific units, or SI units, one of the reasons we use the metric system is that it's much easier to do those calculations and convert from one thing to another. So, in order to convert, whether we're talking metric or American Standard, we need to be able to convert from one thing to another, and to do that we use the factor label method. In chemistry, you'll spend a lot of time working on this. Essentially, though, it's setting up a proportion. So, you set up a proportion. So, for example, if we wanted to find out how many inches there are in 7 centimeters, I need to know how many centimeters there are in 1 centimeter. So, 2.54 centimeters fit in 1 inch. I can set up a proportion, so 2.54 centimeters in 1 inch, and set that equal to 7 centimeters in an unknown number of inches. I can then cross multiply. So I would have 1 centimeter equals 2.57x. Divide 2.57 from both sides. And I would find out that 7 divided by 2.57 gives me 2.76. So in other words, in 7 centimeters I have 2.76 inches. But that's a lot of work. Which is one of the reasons why we don't use standard units very often. Within the metric system, it is lots easier because everything is based on 10. And so 0, 10, 100, 1,000, if I want to take 1,000 and divide by 10, it's 100, it's easy, it's all much simpler. So we can do this in the metric system regardless of what unit we use. We always use the same prefix. So we have kilograms, we have kilometers, we have kiloliters. That kilo always means the same thing. It means 1,000. Okay, so you have this chart in your notes. Unfortunately, I do expect you to memorize it. Keep in mind, though, if you notice in your notes, if we started our base unit, that would be like gram, liter, meter, etc. That's our base unit. It's not multiplied by anything. As we go up, we're multiplying by factors of 10, so 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000, and so forth. But notice we skipped some here because nobody really uses anything between kilo and mega. We just go from kilo and mega. You're probably familiar with those in bytes. It doesn't quite work the same way for computers, but nearly the same. Conversely, going downwards, we're dividing by 10. So 1 divided by 10 is 0.1. 1 divided by 100 is 0.01, and so forth. And once again, down here, we're going by factors of groups of 3, or so 1,000 at a time. The easiest way I've learned to remember them is the mnemonic. I tack on the giga at the end and the nano and pico at the end. I just remember those. And with computers, giga is pretty easy for us, and nano with nanotechnology is pretty easy for us. So if we keep in mind that giga is the biggest, nanos, we go smaller for pico, but you don't really have to worry about that. So giga to nano, we go, many knights hate dragons because dragons chase many men. So giga, mega, kilo, hecta, deca, base unit, deci, centi, milli, micro. When we convert between metric units, we can absolutely do the factor label method. So keep in mind, if I want to know how many kilometers are in 2,000 meters, I can cross multiply. So I set up my proportion, and I get 2 kilometers. But wait a minute, 2,000, 2, I just got rid of the zeros. Notice I went, and when I go from a small number to a bigger unit, my number got smaller. So essentially what I did is I took 2,000, I moved my decimal point over to the left. If I go to a smaller unit from a bigger unit, my number will get bigger. So if I want to know how many meters are in 40 kilometers, 40 kilometers is very big, meters are small, so I can expect my number to have a lot of little meters in a very big meter. So if I set up my proportion and cross multiply, I find out that there are 40,000 meters in 40 kilometers. Again, 40,000, 40. All I did was move the decimal point because I got rid of some zeros. In this case, I moved my decimal point to the right to go from 40, which is where it would have been here. Now my decimal point's over here. So I have a shortcut. I don't know how your chemistry teachers would feel about this, but in life it will save you a lot of time. So if you count how many powers of 10 you have to go, so in other words, how many times you would move the decimal point, you can just do that. So if I want to go from millimeter to meter, that's 3 jumps. Remember, when we get past kilo and milli, it goes by 3. So let's show you some example. We move the decimal point left or right as needed. We're going to move it right if we're going to a bigger number, and left if we're going to a smaller number. And that's a lot to remember, but the easiest way is simply to lay it out and model it. Okay. So if we take a look and we line up our numbers, many knights hate dragons because dragons chase many men. We lay those out there. I put in asterisks or little dots on there so I remember that there's placekeepers that those are going by 3s. So if I want to know how many millimeters are in a meter, I lay out my sequence. I'm starting at millimeters. So millimeters puts me starting at milli, which is right there. Remember, base, deci, centi, milli. So my decimal point started off right here, and I want to go to meter, so I want to go to base here. So I'm going to jump 1, 2, 3 times. So my decimal point started off here in 37, so I'm going to go 1, 2, 3. Now my decimal point goes there, and I fill in the space with a 0. Then I make it meters. Let's take a look at another example, this time going from a very large number, 1.54 kilometers, so that's big, to a small number, centimeter, which is much smaller. So if we start at kilometers here, we're going to go from kilometers to hectare to deca to base to deci to centi. That's 5 jumps. We moved from kilometers towards the right. So we're going to move our decimal point 1, 2, 3, 4, 5 places, add our zeros, and move the decimal point. So that leaves us with 154,000 centimeters in 1.54 kilometers. You can do the factor label, in other words, you can set up a proportion and solve every time, but for me this is easier. Now I need to warn you that almost every year, the most difficult part of the unit assessment for this unit is the conversions, so it will take some practice. Make sure you come see me if you have any questions.